All right, so it's my great pleasure to have Ivan Nikitin telling us about some geometry, and graciously agreeing to speak to us combinatorics as our
yes, thank you very much. I'm honored to be here, and I'm not going to. It's going to be very informal. It's going to be very informal because otherwise I would have to cover like a lot of material, and I have only 1 hour. So I would like to focus on some research I made in this field with some giving you with, of course, I would give you some references. So if you're interested, you can start your own journey in this topic, but I'm not actually going to focus on the history. So for the start, let us start from the like really elementary question. So and feel free to interrupt me and ask questions if you want to. So let's say we have a couple of polynomials. Let's say we have a couple of polynomials, f1 of x and f2 of x. Let it be just a couple of polynomials from like 2 polynomials of the same degree let's say d of the same degree, and let us consider their linear combination. And for now, let's say alpha and beta are just scalars. Let's say alpha and beta are just scalars. So the linear combination of 2 polynomials is again another polynomial. And let's say we for some reasons we want so much to lower the degree of a combination as much as we could. So we might be guessing for now. We might be guessing if the first polynomial is of the degree d, and if the second polynomial is of the same degree, that for generic choice of couple of alpha and beta, the linear combination is also going to be of the degree d, of course, because you can just explicitly represent the highest term of this combination like by the formula f1d plus beta f2d. And if you want to lower this degree, if you want to lower the degree of the combination, you want to set this combination to 0. And if f1 of d is not a power, is the number of coefficient of the corresponding polynomial. If we want to drop the degree of this combination, we want to set this number to 0. And what else we can achieve once we do this? Actually, we can achieve nothing, because if we add another condition to that condition, then for general choice of polynomials, you will have the system of linear equations of 2 variables of more or equal than 2 equations. And you don't have to be really smart to guess that in this case, you will just get their 0 combination of polynomials. On the other hand, so we don't have much power here if we consider linear combinations with just scalars. So now let's say I will not do it
What
again.
do the ellipses? What does the second case represent? The one
there are no second cases. There are only one case. So let's say if we want to, let's say we successfully dropped. Yeah.
Oh, I see. Okay,
yeah. So we successfully dropped their degree of this group of this combination by 1. So now we have a polynomial of degree d minus 1.
Mm-hmm.
If we want to do it again, we cannot do it again, because otherwise we will just have 0 tautologically zero polynomial. So if we take, I will be like super careful right now. And so let's say just extend our powers. So for now, let us take alpha and beta. I'm drawing on a different blackboard, so I use the same letters for different objects for the sake of confusion, of course. But let's all right. Let us be careful. So for now, let us alpha and beta be new couple of coefficients, but they are not just scalars anymore. We take them from the ring of polynomial equations, from the same world where f1 and f2 have come. And in this case, the Euclidean algorithm is telling us that for some choice of alpha, of new alpha and new beta, I know if, of course, if f1 of x, f2 of x have greater common divisor to be 1, we can find alpha, new alpha, and new beta so that we obtain unit as a linear combination of these guys. Doesn't it seem a little bit discontinuous? So let's say D is like, it's large. And let's say we experiment with scalars and we can only obtain D minus 1. And now, being unsatisfied, we take alpha and beta to be polynomials, like any polynomials. Like, let's say we can take any of them. And the algebra for the first course is going to tell us that in this case, we can already obtain unit. It sounds a little bit discontinuous. And let's say, can we find a way to control the situation a little bit more smoothly? So let's say we can do this. And that is just an introductory part. So on this blackboard, I just started to talk about, let's say I assume that we understood everything here. So I can, so
You have 6 points.
all right.
Yes, please do use them.
Control Z doesn't work here, so I can do anything. Okay. Okay, so let's say we have, despite their social media, we have a normal attention span, so we can remember that. Okay, so let us introduce, we have scalars, which are basically the polynomials of degree 0, and we have polynomials of degree.
Can you put up the backboard?
And we have polynomials of degree like everything.
Could you move the?
Because you wrote on the.
Oh, you wrote.
On the stable one.
Okay. All right.
Not at the same time. What did you say?
Sorry, all good.
Oh, okay. So, and we have the set of complex numbers, which are basically like 0-degree polynomials, and we have, on the other hand, we have polynomials of degree like of any degree. So we want to build a bridge between them, so we can control this question more efficiently. So for this sake, let us introduce what's so-called. Let us call it C of x of degree smaller or equal to I don't know, C. So the vector space of all polynomials of degree at most C. And let us introduce another space. Game starts here, by the way. Introductory part is almost over, but this space is going to be generalized in the second part of the presentation. So let us just pay a little bit more attention here. Let us introduce new space. So let's have f1 of x and f2 of x. to be fixed and nice. So let's say they have no greater common divisor. I mean, it's 1. And let's say they have like degree d in common. So I will denote V capital, upper script, this couple of polynomials, comma, C, which is their most, which is the greatest possible degree of polynomials we will use as coefficients. And we will we will leave subscript empty for now. And what is it going to be? It's going to be, again, a vector space of all linear combinations C1 F1 plus C2 F2, such that Fi is in this space. And let us discuss it a little bit more. What did you say?
There's a subscript in the less than.
Yeah,
it's a C.
Si is
No,
S1
that's
or
fine.
S2.
The one to the right, the less than equal to.
Yes.
Missing a C.
Oh, yeah, thank you very much. Thank you very much. Thank you very much. Yeah, and I just realized that it's better to draw 1 here because we are going to consider. Anyway, let it be 1. Let it be 1. Okay, so and we want to calculate the dimension of this space, and well, give me a second. It's lies in C. Yeah, sorry. And so again, that is the vector space in another space of C. Wait, no, of course not. It's a yeah, it's going to be in C square. So it's the subspace of couples of coefficients such that they have this property.
So it's C, but are you thinking the set of pairs, 1 and 2?
C1, C2.
Yeah, I know. Yes, you're right. You're right. That's a great correction. I appreciate that you listen to me so carefully. Well, let me just. Yes, it's going to be the set of couples of C1, C2, such that, yes, you're right, such that this linear combination is a scalar instead of polynomial. And we want to study the dimension of this vector space. And what can we actually say about it? What can we say about it? What is written here is nothing but the set of linear equations, because once we fix C as the maximal possible degree of Ci, we can force this linear combination to have 0 coefficients at all the monomials outside 0 monomial, not 0 monomial, unit monomial, which is a scalar. So what is written here is just the set of all linear combinations, the set of linear conditions on the coefficients of this linear combination. but some of them are zeros. So some of them are non-zero, and some of them are zeros. And if we want to calculate its dimension, it just means that we want to solve the system of linear equations where for each monomial from and C1 F1 of x is going to have degree C plus D in general. So if we want to set this linear combination to be a scalar, this system of linear equations is going to have C, let's say C plus D equations. C plus D equations. And if we want to calculate the space of all non-zero combinations, we must exclude from this space their subspace of all combinations which are tautologically zero. Because because some of them are zero, and we want this linear combination to be one. So the subspace we are looking for, which is giving us the linear combination, which is a scalar, is a subspace of all linear combinations which might be zero. So
Hold on.
What?
Yeah. We just put the board behind.
oh, thank you. Okay, so let's say we have let's say we have a couple of polynomials which has no common zeros. Oh yeah. Thank you. I don't know, maybe that would be multiplied by alpha, which controls that this couple of polynomials doesn't have any zeros in common. So if we multiply, let it be u and v. If we multiply u and v by some polynomials which are of degree 1, we are going to achieve nothing, because you cannot reduce this couple of polynomials to unit using just linear polynomials. So the dimension of this space for some values of C are going to be 0. And when we add additional points to the set of monomials of C and S, at some step, we are going to observe that the space which we have defined here is going to have its dimension increasing. So let us calculate the dimension of V, and let us follow how it is changing when we add extra degrees to the coefficients C1 and C2.
Sorry, I have
For
a
this
question. Also you can write on another board instead of erasing stuff. So are you choosing alpha not just so they don't have roots in
Yeah,
common?
I just want U and V do
You
not
want
have
alpha to be generic,
Yeah,
or-
I just wanted them to be generic, and that's why I added alpha. Because
No, I mean, are you allowing like alpha equals -1? Because that's like a special.
I'm
value you
allowing
really don't
allowing
want.
alpha to be anything if U and V do not have any roots in common.
Right. but
Yeah,
alpha
yeah.
equals
Don't
-1
give don't give.
change the behavior, because when you add them.
Yeah, I
you
know.
get a scalar
Don't
right away.
pay alpha too much attention. I just wrote it here because I couldn't make up a couple of polynomials which doesn't have a common root. So let's say it was just it was just
Can solve.
yeah. So
Okay, so it's
I
not
was
supposed
going-
to be parameterized. by
yeah,
alpha,
I
it's
just gave you this couple of polynomials
great.
to just like a
Yeah, I just,
example which stole your attention. So that was my mistake. So what I'm trying to say that we want to deduce a formula for the dimension of V, and we want to somehow differentiate it with respect to C, so we can understand how this dimension is increasing when C is changing, and we want to understand at what point we can stop so that this dimension is no longer growing with respect to C. So let's go to the formulas.
Ivan, do feel free to use both of those sides as well.
Of course,
Leave
of
stuff
course.
on the board.
Uh,
Please do.
go out of the comfort zone yourself.
Yes.
Yeah. So okay. So let's define a map which is called phi, and which is mapping a couple of polynomials of degree C. I is from. So get used to this space, and let us map this couple to C1 F1 plus C2 F2, and let us consider the second map phi, which is taking a polynomial, and consider which is consisting of monomials. Let's say A from the support of P, and let it map it to another polynomial, but A is going to be of the same set from the same set of monomials but outside 0. So what I'm trying to say, let us identify the set of monomials of this polynomial with integral points of integral numbers, and we will call the support of P the set of integral numbers which are included as P. So let's say if you consider the polynomial 1 plus x, then its support is going to be like this couple of points, 0 and 1. If you have it minus x cubed, it doesn't have to be continuous. So we must add 3. Okay, and if we map this polynomial to another polynomial where we do not include 0 among its monomials, we say that the phi of it is going to be the same polynomial but without 0 term. It's not 0 term, scalar term. Okay, and
P minus P is evaluated at 0.
Hmm?
P minus P evaluated at 0.
P minus P evaluated at 0. No, we do not evaluate anything.
No,
We
but
just-
actually you can define this map like this.
Yes, you're right. Yes, correct. That's correct. And from this point of view, the dimension of V1 is going to be the dimension of the kernel of P minus the dimension of the kernel of phi. Because we want to find all we want to find the space of all non-zero linear combinations of these two polynomials, which support is just a scalar term, but we want it to be non-zero. Why do we subtract the second term? Because it might happen that we do not.
I compose with V, the kernel
I
of I compose with V.
Yes. You know about my talk more than I do. You know about it more than I do. Yeah, thank you. So what we are trying to achieve and why do this formula make sense? Because it's implicitly depending on C, and for some low dimensional C, this dimension is going to be just 0. But while you are adding extra points to C, at some point you might start noticing that this dimension is starting growing. Let us demonstrate how it works. Let us demonstrate how it works. If what we are going to do is just express what's happening right now as a system of linear equations. So let us first emphasize that this value is depending on C. So let's add C here. Somehow we can add C here and C here. So if we calculate this value at some point C, what we are going to have according to this map, we are going to have some polynomial. Of course, it's going to consist of monomials, and each monomial will be multiplied by a linear combination of coefficients of C, coefficients of C2, and coefficients of F. And if we want them to be 0, then each monomial transforms into some linear conditions imposed on the coefficients of C1 and C2. So each coefficient from 0 to D plus C turns out to be a linear condition imposed on the coefficients standing next to each term. And in turn, it's corresponding to some linear equation from this system. So we can encode the system of these linear equations by a matrix whose columns correspond to points of terms of each C. And its rows are corresponding to conditions imposed on them. So we have a system of linear equations. In each row, we are going to have coefficients depending on the coefficients of F. and in each column we are going to have and each column is going to be corresponding to some coefficient of C, which is unknown, which we would want to find, so we can understand how this dimension is changing.
When you write terms of C, is there a subscript?
Yeah,
Okay, just do.
terms
there's
of
multiple Cs.
C1, C2, I
Okay.
would say.
Perfect, thank you.
Terms of, so we have, yes, we can calculate how much columns we have in this step. We have C1 plus C2, which is nothing but 2 C columns, and we have some number of conditions. We actually have, like, starting from 0. I'm not good at math. I'm not good at calculating. Starting from 1 to D plus C. If we want all of them to vanish, we are going to have D plus C plus 1 conditions. So yes, we will have D plus C plus 1 condition, but one of them will only show here, because in the kernel of pi, we want all this combination to be 0. In the kernel of pi composing with pi, we only want everything to vanish instead of the constant term. And I'm not afraid to repeat myself. We are doing all this work to understand how we can differentiate this value with respect to C, because it's the only object here which is changing. All right, so we have C1 plus C2 set theoretically to C columns. We have D plus C plus 1 conditions, or we can have D plus C conditions if you are not including all the conditions. You can only consider conditions starting from degree 1 to degree D plus C. Okay, and you might have noticed that for some unknown reasons, I have drawn this cross in the middle of the matrix. Why did I do that? Nobody knows, but you will find out very soon. Let's say we have C1 and C2 of degree C, and just like I just told you, we want to add some extra term to C and understand how this matrix is changing. Indeed, what we are going to have. So here, let us call it omega of C. And now let's say we have added one single term to each of C. In this case, we will have some D plus C plus 1 extra condition, and we will have 2 extra columns, and we will have some new condition, one single condition, because we have only added 1 point, 1 extra term, 1 point to the support of C, which means one single extra term to each of C, which means after the multiplication of C and F, we will have 1 extra term. And terms, as I just have explained to you, are corresponding to conditions. So extra term of C. And so we have two new columns. We have 1 extra condition. So we have some numbers here. We actually know what numbers are they. They are the biggest degrees of F. And we will have some numbers here because their previous let me just we will have some numbers here because of this extra terms in C. We will get new linear summands in the previous conditions which we imposed on previous terms. But we will not have all coefficients from C in the new condition, because this condition lies outside the area of power of the previous terms of C. So we will not add extra numbers at the bottom of omega. So here we will have 0. So what I'm just saying, adding new terms to C carefully will make this matrix to have a very convenient form, and we will understand why it's so convenient very soon. So in our notation, this matrix is called omega of C, and that means the bigger matrix. Let us call it C plus, I don't know, Q, C and Q, because we have added that extra term to it. And let us call this small 2 times 1 matrix delta omega. And we can see that the rank of omega disjoint Q is bigger or equal to the rank of the previous omega plus the rank of small omega, of delta omega. Because we have zeros in the intersection of old omega and delta omega. So we can estimate the rank of new matrix by this inequality. You wanted me to use all the variety of black bars. So let's do it. And as we are playing like we try to differentiate something, let us say that in this case, delta of rank omega of C, which is equal to new rank of C and Q minus rank of old omega, and that by this inequality is bigger than the rank of delta omega. So I'm not trying to slip your attention by changing the order of letters. It will have a really important meaning very soon. So now, what are we going to do? Let us just substitute this information here. Not immediately, but we will. So for now, let us observe this term. It's going to be the easiest one. Why? Why am I saying this? Because kernel of phi is just the set of linear equations where
Other board.
what do you mean, like
The one behind, just move it up so that you can still see.
yeah, okay, thank you.
Yeah.
No, thanks too. And kernel of phi, it's more convenient to consider that as not the set of linear equations, but it's more convenient to consider that as one algebraic equation. Because we know that the greater common divisor of f1 and f2 is 1. So we can give explicitly the solution to this system of equations. So it's going to be C1 is equal to lambda f2, and C2 is equal to minus lambda f1. Because if there are greater, do I really need to explain this? If greater common divisor of these two elements is 1, then you can just say that C1 f1 equals to minus C2 f2. And since this side is divisible by f2, then one of them is divisible by f2, and from this you can deduce that this formula. And that means that lambda can be chosen arbitrarily if it's even possible to find such lambda. So the dimension of kernel of phi of C, and we consider everything depending on C because we are playing like we try to differentiate everything, is going to be just the dimension of lambda. Oh, it's going to be just is going to be equal to just the degree of lambda plus 1. Yes. So it's going to be like C2 is this degree C, F1, just like F2, they have degree D minus D, and plus 1. Yes, I think so. So we have found the dimension of the kernel of phi, provided that it's even possible to find this kernel, because for some small degrees of C, C cannot be represented to this form because it might have degree too small to be multiple, to be the product of F and something else. So for large C large enough, for C large enough, we can give this formula. It's C minus D plus 1 or C minus D, I'm not sure. C plus 1, I think it's C minus D plus 1. And
I
What-
don't know if it's plus or minus 1.
what do you say?
I'm hesitating
correct.
about plus or minus 1.
Yes, I'm always hesitating about everything. Yes. So because yes. So
What do you use that for? Use one device.
yes, thank you very much. Thank you for guiding me. Thank you for guiding me. Well, we have this formula, and again, we are playing like we try to differentiate something. So we can say that the delta, so we move from exact formula, we move to difference. So delta of dimension of V1 of C is equal to delta of the first term. And this term is going to be what, according to the linear algebra, is going to be the number of all variables, which is 2C minus rank of omega, actually, rank of omega of C minus delta of the dimension of kernel of C, of phi of C. Let us substitute all the information we have found here. Oh, sorry. Delta of this bracket can be expanded to be true delta of C minus delta of rank omega of C minus delta of the dimension. We have already found the dimension. It's C minus D. C minus D minus plus 1. We are not sure. We're not sure plus or minus, but it's not so important. So we can see that true delta C is just 2 because delta C is 1. We have added one single term to each of C. So delta C is 1 minus delta of the rank is minus delta of the rank from this inequality is going to be minus is smaller or equal to minus rank of delta omega. So I use the sign of inequality here. And instead of this term, I use this term, minus rank of delta omega of C. And delta C here, this is constant, and delta C here is just 1. So in the end, we will have 2 minus 1, 1, and minus rank of delta omega of C. And this term is going to be much easier to study than the entire matrix because we know all the dimensions and all the coefficients of delta omega, isn't it? So because here we don't even know what numbers are going to stand here. We don't know how to control, or of course we cannot control anything. That's just an illusion of control, but it's enough. And it's enough to make some estimations because we can estimate this formula, how it's changing if we add extra terms to C, and we know how to estimate it by the rank of delta, and we know everything about delta. Okay, and let us remind ourselves what is delta omega. Delta omega consists of yes, exactly. So you have changed me as a person today.
Could you pull the one from behind down? The one behind, could you pull it down? Yeah, little more change. Yes, thank you.
Yeah. I have so much to learn. Okay, so let's consider delta omega. And we know everything about it. It's going to be F D, F1D, F2D. Nothing like that. So, and that's just rank 1 matrix. Nothing more. So its rank is just 1. So substituting this precious 1 here, we can find that it's 1 minus 1 and it's 0. What does it mean? That means that once C is big enough, we can show that adding extra terms to C, we will not change the dimension of this space because we just estimated that its derivative, because we are playing like we are taking some derivatives, because we pretend that we vary C and we extract some formulas from. And so we can see that starting from some C, its derivative of this formula is going to be 0. So we can say that to represent 1 as a linear combination in commas, because we take coefficients from the space, from the restricted space of polynomials. It's enough to take polynomials of degree at least such that of degrees of values such that we can use all these computations. Where did we use some where did we have doubts about our calculations? Nothing, nowhere actually, except this place where we were frightened of not having enough terms in C or in C, because C here is represented as product of F and something. So we can guarantee that once the degree of C is at least D using this.
D minus.
Hmm?
D minus.
No, if it's -1, then you will never represent, you cannot represent D minus 1 polynomial as a product of something and degree D polynomial.
Yeah, but then that's zeros.
Hmm?
The formula is true because the dimensions are zero.
The formula is true, but it's not possible to obtain D minus 1 polynomial as the product of degree D polynomial. So all our computations have actually started once we grew C enough to satisfy these equations for some lambda. So what we have found that we can not only guarantee that unit is representable as a polynomial combination of F1 and F2, we can also restrict the dimension of a vector space where we could find the solution.
Wait,
what
sorry.
are we doing right now?
I have a question. Sorry, so are you claiming that V1, F1, F2, C, the dimension of it eventually stabilizes if C is sufficiently big?
Yes.
But as I increase C, don't I have all of my previous solutions?
Mm.
Plus, I can add stupid things from the kernel. So I would expect it to grow like linearly, like every time C increased by 1, you get one more thing there.
Yes, you're right.
Huh?
You're right. You're right. And explanation is that well, I do not put my responsibility on you. I say we because it's just a scientific tone. That's because I used V1 while it's not V1 actually. I made a mistake. I made a typo. It's not V1. That's a target space of all such scalars we're looking for. So I made a mistake. You're right. I made a mistake. Sorry. It's not V1. We are using V1 as the source of all materials for this space, but this space is some, I don't know, let us call it A of C. A of C is the space of all linear combinations which can be obtained by taking C1 and C2 from V. Yes. I just made a typo. Yes, I take full responsibility. I can explain it. So let's say we have worked out what we are doing with V1. What we are doing with V1 actually, oh my
I
goodness.
mean, are you saying you're just quotienting
Live,
out?
it's that's crazy how
Are
it's
you saying
fast.
you're just quotienting
Yes,
out by these trivial
V1,
solutions?
V1. Yes, there is no mistake. It's just a typo in this formula, and I take full responsibility here. V1
I didn't understand the
is
dimension of
yes,
kernel of
yes, V1. Yeah, thank you, thank you for listening me so carefully. So V1 is the space of all C such that we take them to construct linear combinations which we want to be just scalars. And we want to calculate the dimension of this space of scalars, which might sound strange because the space of scalars is either trivial, which means 0, or just one-dimensional. But in this simple example, we can work with this 1 or 0-dimensional space, and we can expose all the theory we can apply to higher dimensional case. So I'm so sorry. I'm so sorry for this typo, because it's really just a typo. I just forgot to say one single line of text. We take coefficients from this space. So we want them to to break down what?
Write down.
Write down the formal definition of AC.
Of A, okay.
Thank you.
No, thanks to A of C is
B of B1.
is just C1 F1 plus C2 F2, such that the couple of C1 C2 is from
B1.
B1. Yes. Yeah. Thank you. Thank you very much. Thank you very much. I remember how I studied all this for the first time, and it was a nightmare because you have like a lot of linear maps. So thank you very much. Thank you very much. I'm so grateful for pointing out this mistake. So that, okay, I'm not trying to hide anything from you. That's just a habit. So what we have done for this short hour, we have shown that we can turn the non-constructive question whether such C1 and C2 even exist to a constructive question, how we can find them, turning a question about abstract algebra, and all the questions from commutative algebra are some sort of infinitely dimensional because the set of all polynomials is infinitely dimensional. And we have found a way to turn this question into infinitely dimensional, provided we can give some geometric explanations why we can stop at some certain point. And I will use a few minutes available for me to show the same question in higher dimensions. I will, oh my God, I have, well, I think, okay, so let's say for now that F1 and F2 are from the space of all polynomials of 3 dimensions, of 3 variables. And what do we use instead of degree when we have multiple variables? We use the so-called Newton polytope. Which is the convex closure of support of F. So let's say we have, I don't know, let's say we have a polynomial 1 plus x squared plus y. Its support is going to be the union of these 3 points. And its Newton polytope is going to be like this triangle. And the same is going to be for higher dimensions. And let's say they have the same Newton polytope, let it called B. And we have learned a precious lesson from the previous example that when we add new terms carefully, we can control how their target dimension A of C is changing. And we can analyze when we can stop so that A of C is not changing anymore. Yes, so instead of just one-dimensional polynomials, we are going to have C1 F1 plus C2 F2, and C1 and C2 are also from the set of polynomials in 3 dimension. And how can we add additional points to the supports of C? There are different ways to do that. Let's choose the way when we take C, let it be just a support of Ci. And what is the most convenient way to add extra vertices or just extra points to C? Let us test the situation when we add an extra facet to it. So let's say it's a 3-dimensional cube, and we add an extra facet to it. What it means in terms of all the machinery we have studied so far. We will have the same formula, and
So you're
The
still
fir-
trying to express one as a linear combination or a scalar as a linear combination?
what did you say?
With this
sir?
higher dimensional setup, are you still trying to get one as the linear combination? Or like a scalar as a linear combination? Or are you generalizing that subscript?
I'm generalizing everything. I just want to show the geometrical picture which is standing behind the computations,
Yeah, but
because I don't have enough time actually. So
Sorry.
you want
so-
me to be more precise?
Maybe the question, tell me if I'm wrong. Are you still looking for combination C1, F1 plus C2, F2 that land inside the complex? Is that what you? Yeah. Is your
I
space
just-
V sub 1 defined in essentially the same way, except your polynomial ring
It's
has more?
defined. I didn't say it. I haven't said it yet, but this time,
Uh-huh.
what's the difference between one-dimensional case and a multiple dimensional case? In one-dimensional case, if two polynomials do not have common multiple, so their greatest common divisor is 1, in one-dimensional case, they will not have common roots. In multiple dimensional case, they might not have common multiple, but they still have a variety of points as the set of common roots. So here, instead of just set of scalars, we must change this condition to fixing some subset of points from this space of integral points, and we want to impose the condition that the support of this combination is a subset of A. I use, of course, I use this for the sake of confusion. For the sake of confusion, I use the same letter. Let's do it. F is a facet, so I don't know. W was somewhere. G, yeah. So In the first example, G was just a single point, and this power was equal to 1. And here we impose different conditions. So we require the support of this linear combination to be inside of some fixed G. And we want to find, and we want to understand how can we find some careful way of adding extra points to C so that we can calculate the same variable, the same value depending on the number of points in C and depends on geometry of the support of C, so that we can make the same conclusions starting from some position, starting from some geometry of C. We can stop and we can just deduce that the dimension of A is not going to change anymore. Well, so their purely algebraic question, which we have stated, is now transformed to another question of finding this extra careful way of adding extra points to C so that we can write down the same formulas and make the same conclusion. So just give me extra 2 minutes. I know I have already holding you too much. So let's say we add an extra facet to the support of C. What is going to happen here? Omega of C is not changing. Here we will have, instead of just 2 points, we will have 2 times delta C points, where delta C points is the number of integral points in this facet. So this matrix is no longer 2 times 1. It must be complex. And we have added extra conditions, which the set of which consists of all new monomials which delta C is bringing to their support of C1 F1 plus C2 F2, because each phase will be multiplied by F1 and each phase here will be multiplied by F2. So we will not only have new monomials in C, we will have a lot of new conditions in here. But it's still convenient because we will have this pressure 0 under the omega of C from the previous state of C capital. Why? Because adding new terms to their multiples, we will not have the old terms in new conditions. That's impossible. We can only have new coefficients in new set of conditions. That's why we can still have this inequality, and we can estimate delta rank omega of C like it's minus by minus rank of delta omega. And we can study delta omega separately. So we will have oh my God, I have erased everything. Don't worry, I will stop very soon. So delta A is going to be the same. It's going to be delta. It's going to be delta of true C minus rank of omega of C minus delta of the dimension of kernel of phi of C. So we know that delta of 2C is going to be 2 this number, which is the number of points in this extra facet, minus this value, which is now independent on everything which was happening before, because we have isolated this little matrix, minus delta minus rank of delta omega of t. And this value can also be computed because we now have that C1 is lambda F2 and C2 is minus lambda F1, where lambda is any polynomial with their support C minus B, where this fancy sign means the Pontryagin difference. Let me give you a definition. So if we have two sets X and Y, their Pontryagin difference is that the set of all integral vectors from the lattice so that Z plus Y is a subset of X. So it's the set of integral vectors which shifts Y to a subset of X. Just because C1 is a product of lambda and F2, you can deduce that in this case, each monomial of lambda must shift F2, must shift the support of F2 to the support of C1. And that's why lambda is any polynomial with the support lying inside of this, the so-called Pontryagin difference. There are some tiny moments in this definition, and in applying this formula, it depends on convexity actually. So for some choice of C and B, I think, well, I'm actually sure this formula is not valid in this situation. But for simplicity, we assume that C and B are convex. So let's say what's going on here. So we have computed that this dimension is equal to the Pontryagin difference. And that's very interesting. So let us use it here, minus delta of the number of integral points in Pontryagin difference. And what is that? What is that? It's the most interesting part, because what we have here, 2 times delta C, is representing all the new variables in new facet. And rank of delta omega of C is the rank of this tiny, though very important matrix. And the difference between true delta C and the rank of its matrix is the dimension of the set of solutions of the system of linear equations, which has the following meaning. We take only new monomials from this facet. We impose only conditions we have taken by adding new monomials. And we calculate the dimension of all coefficients from C as though we do not have anything before that. So what does it mean? That means that we group together all the monomials of C1 F1 plus C2 F2 which lies inside delta C plus their facet of B with the same normal vector. So let's say delta C has some normal vector alpha. So here we are taking all the monomials here, which lies inside a hyperplane, which is the facet of the support of C1 F1 with the same normal vector as delta C has. So here is it can be reduced let's indeed write on that and that would make more. So we can apply alpha to all these terms here, and it's going to be C1 alpha F1 alpha plus C2 alpha F2 alpha equals 0. But this formula is actually the same kind as it is. And we can say that the dimension of the set of its solutions can be taken by the same von Tragen difference, but applied not to C and B, but to their facets of their with the normal vector alpha. So from what I just said, we can deduce that true delta C minus rank of delta omega of C is equal to the C alpha, which is delta C actually, von Tragen difference beta B alpha. So we can see that this formula is going to be like delta C minus B alpha minus delta of C minus B. So let us think of the geometrical meaning of this inequality. What we have here, that is the number of integral vectors which can shift B alpha, the facet of B with the normal vector alpha, to delta C with the same normal vector. And this term is responsible for how the number of all integral vectors which can shift beta to a subset of C changed when we add delta C. So we can see that this set of vectors is a subset of this set of vectors. Because if you can shift the entire polytope to another polytope, you will, of course, shift its corresponding facets. So from this formula, it follows then we can stop the procedure of adding new points to C if we have found a careful way to add new facets to C so that new ways of adding the corresponding facets of B to C can be extended to their ways of shifted B to C. And it's only in their dimension 3. And in higher dimension, don't worry, I will not tell you about this right now, only if you want to. And in higher dimension, we can use this partial case as an induction base. And we can substitute all this data to causal complex if we consider a bigger tuple of polynomials, not only true. If we consider a lot of polynomials up to n, we can construct a causal complex for them. And we can use this data and this geometrical intuition and this geometrical actually it can be turned into a theorem how we can extend what kind of C we should choose and how we should move its facets so that this term is always 0 starting from some point. We can reformulate it, this geometrical intuition as a theorem, and in higher dimensions we can use it as an induction base to plug it into a causal complex and use it to deduce some formulas which look similar but in higher dimension using their causal complex. Yeah, I know I have violated the restriction of time, but I hope that was at least funny. I hope that was at least funny. And again, we obtained this like again. I think that is surprising that everything depends on can we extend how we shift facet to facet? Can we extend it to how we shift the entire polytope to their entire polytope? Yeah, sounds a little bit homological because we want to extend something, but we're not sure if we can, but we can actually. But I have this seminar is too short for me to tell you the entire story. Yeah, so that's all. The torture is over. Thank you. Yeah.
Any questions?
Yeah. I would be happy to.
In the one dimension, there's a explicit bound of the exact C, such that you can stop growing.
Yeah, that was D actually.
Yeah, and what about higher dimension?
About higher dimension, well, let's just. Yes, it might depend. It depends on B, but we can give an answer in terms of B. So if you have this result is actually under the review now. It's under the review now. But if you have a tuple of polynomials, f1, f2, etc., fk, where k is at most n-1, and a and b and a is a couple of polytopes in Z, and then any G which can be represented via linear combination of these polytopes such that support of G is in A, then we can find then, well, let me just, I'm a little bit fuzzy right now already. So if we have a tuple of polytopes at most n-1, and if we want to find a vector space of all G of this form such that the support of G is in A, it's enough to take C to be T B such that A plus probably some integral vector lies in T B plus B. So if we can shift A to this polytope B plus TB for some real non-negative T, then it would be enough to take coefficients from TB to cover all such G with that property. So, and T is not dependent on G, of course. It only depends on A and B. So if you can find, of course, you can find T such that A plus some integral vector lies inside TB plus B, then you can find the set of all such G with the support in A, taking only coefficients with this support. Yes, and of course, I forgot to say that by this plus, I mean their Minkowski summation. But I didn't use it during the talk, so it's not a big deal. So yeah, when I say plus between two polytopes, I mean that I take all couples of points from both sets, add them together, and I combine a new set out of them. And Minkowski summation, and Van difference are sort of inverse to each other, because if you take C as a Minkowski sum of B and something else, and you subtract B, you will likely obtain A. Okay. Oh, as I said, that's a complex topic.
That's the result of Kubansky.
Sorry, what?
That's his result. That's Ivan's result.
Yeah, that's my result. It's just under the review. So there is a tiny microscopic possibility that I'm lying to you, but I'm almost sure that I'm not.
Okay, let's delay any further questions to after my applause.
Thank you.
Thank you.
Oh, I will sleep peacefully.